I'm pleased to introduce Dr. Kathy Geiger from the University of Delaware, who's going to talk to us today. And you can see the title of her talk up on the screen now, so I'm not going to repeat it. But just to say, Kathy's been involved in Arctic and Antarctic sea ice research for about 30 years now. Her main interest is in the sea ice thickness distribution and the processes that contribute to the sea ice thickness distribution. And at the risk of telling me I'm wrong, I would say that Kathy's focus has primarily been on the dynamics side of the sea ice thickness distribution equation rather than the thermodynamics. And so to avoid making any further mistakes about Kathy, I'm going to let her continue now. Please go ahead, Kathy.
Thank you, Martin. That was a very nice introduction, and I want to thank also Jessica for coordinating and the pre-planning sessions. That was wonderful. And I also really appreciate this new form of green technology because it helps people like myself who are juggling on a number of fronts to be able to attend today where I can't usually get to AGU these days. I would also like to thank Polar Programs of NSF, especially Bill Wiseman and his team, and Hetty Edmonds and Peter West, who served as my program manager during this project that I'll report to you on today. I understand, Neil Swanberg, you're on the line, and please convey my appreciation to the funding that you provide so that I can do research like this. As a roadmap of what I'll talk about today, I'm just putting up some bullets here to give you a sense of the flow of the talk. I'll begin with an overview of the situation, why I am calling the sea ice thickness distribution a Rosetta Stone. It's quite ironic, perhaps, to some. And then, more importantly, getting to the main science, why is it so hard to match these results? And a heuristic model to explain it, a real data demonstration to see what I'm really talking about, and then a diagnostic tool that my team and I have developed to look at this problem, and then finally impacts and summary. And so whether you were basking in the Christmas sunshine due to Superstorm Frank last year, or you were unable to get to work last week because of Jonas, one thing is becoming very clear. As we move along, the world's weather is connecting us all. These superstorms are getting stronger and more frequent, and so everyone's life is just getting a little more complicated. And so you're wondering, well, what does sea ice thickness have to do with this? But I thought the opening was quite appropriate after last week, and now I see, thanks to Martin's pre-discussion meeting on these new directives and priorities, that connecting to the larger picture is very important. So I wanted to make that point. And so first of all, bringing the connections between the poles and these storms by way of sea ice, I thought I would begin first by explaining to you about the sea ice itself. And as a sea ice geophysicist, I specialize in properties and processes, so I'm not in a position to postulate any grand solutions to this growing problem. But what I can do is explain the role of sea ice in this process, and I can explain where some of the confusion is coming about, especially as we try to measure and characterize what's happening. So let me start by explaining, as you can see in this figure, I'll take you on a little journey here quickly. This is a radar sat image where the little red box shows where we've done research in 2007 during the International Polar Year. And this is the little ice camp we were on, which was, you can see by the leg sizes, about 1 kilometer length measurements, and there's our little huts that were on the ice. And you can see in panel B, this was a submarine transect, thanks to Her Royal Majesty's Tireless, which surveyed beneath the camp at about the same time, though we're not allowed to say exactly when. And you can see in the radar set image, especially in the B panel, there's a lot of white, and this is the multi-year ice, and then the darker black in this scene from radar is actually the first-year ice. So you can see we're at nearly 100% ice coverage. This is a continental polar climate. You can see there's a prominent crack here where a little lead would open up and let a little steam out, but otherwise this is a primarily sealed system between the air and the water. The ice provides a very convenient polar barrier. And so when we want to actually measure the ice thickness here, what we do is we gather samples. And for example, the light blue here, you can see the statistics we assemble as we gather more than 1,000 samples along these transects with electromagnetic and induction instruments and drilling. And you can see how they compare quite well when you line them up, scaled appropriately, against the submarine data that was covering a 20 by 20 kilometer area versus our small little 1 kilometer radius or 2 kilometer by 2 kilometer box here. There's a couple things I'd like to point out. First, not only do you notice that the peaks line up approximately at the modes here where the thermodynamic thickness is represented, but you'll also notice that if you see that this N at 2 kilometers is the submarine data that was right underneath the camp in the same area, but the statistics don't look the same. And what we've learned from that is you really need at least 1,000 points if you're going to accurately sample the sea ice. If you only have a couple hundred points, you just don't have enough material to accumulate the statistics. But when you get up to 1,000 or almost 5,000 points, you really get a good sense. The other thing I want to point out is that if you notice this shape, this distribution curve is letting us accumulate and count what is the total amount. Once you average it all, once you accumulate all these, you can get an average estimate of how much ice is there. So that the light blue here shows that the average thickness, once you include all these categories, is about 3 meters of ice, and that compares very nicely to the submarine data. So that whether you're at a 20 by 20 kilometer box or a 2 by 2 kilometer box, we're finding very strong agreement. And that's because we're using this thickness distribution as the decider or the calculator for how much ice is at different scales. And the last thing I want to point out, which will come into play a little later on, is the fact that there's this very strong mode here at the end, and this other one that's sticking up here. And this actually represents the amount of ice we can measure down to from 0 to about 8 meters with on-the-ground electromagnetic induction instruments. So we wanted to see what we can accumulate up to that point and what all these little tails of information sum to. So while this tail doesn't look like very much, if you actually count how many values of thickness are in this tail, you'll see it accumulates to a very large number. It's 7% of the data. And while that seems small, there's a lot of mass in these thicker amounts. And I ask you to reflect and keep in mind that if you start to truncate your data, you have, if you truncate your data, you have a large number of values here, and then they kind of counterbalance against the average mode of values here. And when you have data distributed like this, it creates a very interesting situation. You actually create a bimodal distribution of data where you have 2 primary modes. You have where a lot of the thin ice is and a lot of the thick ice is. And I ask you as the talk goes forward to keep this in mind, because this bimodal distribution is creating some very interesting situations as we try to analyze our data going forward. But the most important thing to take away from that is that this shape, this thickness distribution shape, is what lets us explain how the characteristics of sea ice are categorized. We can tell that the thin ice is new and it's recently formed. The main peak where everything is sitting is where the thermodynamic ice is formed, and then the deformed ice at the end is where everything kind of gets all rubbly and ridgy and others. So what does that tell us? Well, it tells us that sea ice has a thickness dominated by this shape, not only at 2 kilometers and 20 kilometers, but it has this characteristic shape over a large range of scales. In particular, it's quite notable that sea ice has a vast range of scales, 7 orders of magnitude or more, and there are very few geophysical materials on the planet which let you steadily look at 7 or more orders of magnitude. And so this is what makes sea ice such a fascination to many of us who are in the geography world. And the reason why you can do that is because most of the features are small scale. Most of the roughness that's in sea ice are these little bits and bumps at very small scales, ubiquitous everywhere, most of them being the ridges, which are only 1 to 2 meters or less than 10 meters wide. And so because of this, I am calling the thickness distribution, and my colleagues in our paper, the Rosetta Stone of sea ice, because not only is it a great translator between scales, but the sea ice thickness distribution tells us how well the sea ice is operating as a gateway, because as you saw in that last picture, this continental polar shape is what, or the presence of sea ice is what makes the Arctic a continental polar climate system. It's isolating the 2 large systems of the ocean and the atmosphere, and in that sense, we really use it as a thin membrane that separates 2 large systems. Now, as sea ice is a gateway, it works a lot like a battery. In fact, if battery technology could mimic sea ice or ice of any kind, glacier ice especially, we would solve the energy storage problem as we go forward with solar. You see, the amount of energy it takes to create ice at the melting point, and that's what's called a phase change, where you actually change it from ice to water or water to ice, is 80 times more energy than the amount of energy that just heats water 1 degree, and that's the same amount of it. And so if you think of this 80-to-1 ratio in terms of a little thermometer, what you realize is that the phase change is happening down here around 0 centigrade. It's the same amount of energy as if you brought that same piece of water 80% of the way to boiling. Or if you had 1 meter of ice and you had the same amount of energy, it's like adding 1 degree of Celsius to 80 meters of water. And from a layman's term, putting this in relationship to things like furnaces, you can see that the amount of energy in this is substantial, and it could easily compete in U.S. markets if we could figure out a way to not only have it take away heat, but to generate heat effectively, besides just melting all over the floor. But anyways, this is a very important point, because what sea ice is, what the thickness distribution is not only a Rosetta Stone that lets us evaluate the inventory, but it lets us relate the inventory of types of ice to the thermal storage capacity of the ice and how it regulates conversion of energy at the air-sea interface. And not only can we use the distribution as an energy gauge, but as Martin suggested with the deformation, we have a similar distribution which lets us understand what is the relationship between the strength of the ice at the different thicknesses and how that strength holds the ice together so that it can interact with the air-sea environment, especially in terms of how much access does the sea ice allow the water and the air to engage in. And so heading into now where's this going? Continental polar, I would just like to contrast it for a minute to another type of climate category known as maritime polar. And what you'll see here is a little animation. This is from the sort of stomping grounds where I grew up, and why I've become a polar investigator, is because when you don't have that sea ice, you can have effects like this developing, where the water and the air are not separated by the insulation of sea ice. And so this can cause rising and movement of moisture from the lake up into the atmosphere, and because the triple point of water is at the freezing point, then you can have snow, vapor, and air, and solid liquid particles, all three phases of water coexisting near freezing. Now, what you don't see on this screen that's off screen is that this kind of activity can generate snow at a rate of about 1 inch an hour, and probably something like this is what the Atlantic did over Washington, D.C. last week. So I thought I'd throw that in there because it was important to explain how the maritime polar climate does impact human infrastructure. Now, why am I talking about that, and where is this going? Well, Suk-Young Lee gave a very, very nice talk last fall through the same IARPIC talk, and she showed thermal plumes of warm, moist air rising into the atmosphere, very similar to what you just saw there in that lake effect over Lake Ontario. But in her talk, it was not Lake Ontario. In fact, it was the DOE arms site at Barrow, Alaska, and she was trying to figure out through her model what exactly was going on with these thermal plumes. And essentially, the bottom line of what's happening from a climatological standpoint is that the Arctic is transitioning from a traditional climate category we call a continental polar to a maritime polar. And what I'd like to do now is work with Jessica a little bit to show you an animation. This was December of 2013, and I want to show you when we were in there at the spring before in March, exactly what this looks like when it's breaking apart in the Arctic ice. So I'm going to mute my phone and turn on the sound on my computer. So if you'll just bear with me while I try this technical. Jessica, if you could you manually switch the audios, because I seem to be having a hard time finding them.
I can't actually switch your audio for you.
Okay. Let me see if I could just find it here. Just a second then. I'll just start. I'll leave the PowerPoint for a second. I could just figure out, okay, I'm in the Webex. Let's see, how would the Webex, I don't think I can find the Webex voice. Well, perhaps the telephone can pick this up, so I'll just run the movie. But anyways, what you'll be seeing is an area of about 1 million square kilometers in the Beaufort Sea, where the sea ice moved or transitioned from a maritime to a maritime polar. Now I'm just going to step back a minute here. And if you'll notice here, and this was also put out by the NASA team, these large gray areas here are actually open water where that same rising of steam is coming off of the ice. Now, what's very important about this is the fact that this is happening in February and March. This is not April, this is not May. And so these conditions are not occurring during spring breakup, these are occurring in the winter. And that makes the need to understand the ice strength much more important today than ever before. So I'll just get back onto where I was. And so in terms of everyday life getting complicated, what we're finding is that things are getting more complicated because the ice is getting thinner and weaker, and this is turning the dry, quiet Arctic into a turbulent, wet, new lake effect region. And compared to Lake Ontario and Lake Superior, the Arctic is a very big lake. And so in terms of an energy gauge and how it operates, what we can do with this Rosetta stone, and especially in combination with deformation, a deformation stone, if you will, is to figure out how the rates of energy are changing and how they're impacting the storms. And while we don't have all the answers, we're starting to get some of them. So in particular, one of the projects of SEDNA was to quantify this mass balance and see what was going on. And the biggest thing we became concerned about was, why can't we get sensors to match up? We had coincident aircraft, helicopters on the ground, and AUVs, and we were still having a problem matching everything up. We had very good GPS, and we were really beginning to scratch our heads about this. And what we came to the conclusion of was that within this area we're studying, there are a lot of scales. And whether you're measuring with a satellite, an aircraft, an AUV, or a submarine, or even on the ground with the ground truth, the size of the scales were causing differences in the results. And in fact, the uncertainties were matching up with the scale of observations. So we were concerned about what is going on and how can the choke point where we have the ground truth help us to answer these questions. And so what we began to do was look at the sea ice from a geometric roughness distribution, where most of the features are. And we realized this shape, if you look at it from signal processing, is a perfect candidate for a process known as spatial aliasing. Because aliasing is caused by truncating a signal at a certain, well, in time space, a certain time sampling, in this case, a certain 1/over scale. And once you put a lot of things that are undersampled or not sampled correctly into lower resolution, you alias. And so we were thinking, this really could be the source of the problem. Well, it's got good news and bad news, but we looked into it further. And so to explain what we're talking about, I want to show you this little toy. Jim Overland was a very good supporter of, he taught me so much about just explaining things as simple as possible. So if we take a ridge made out of a triangle and we start to sample it with a little instrument that looks like this little blue arrow, we can see that when you place it in a distribution, you have two places. And if you remember that bimodal distribution, this is again that case where you've got data at -1 and 1 showing no thickness, and then you've got 1 point showing this thickness. And if you measure with a bigger footprint, you get a slightly different answer. In fact, you get something in between, which is the average. And then you realize, well, the volume's conserved, so we're fine. But what's happening is that there's a filtering going on, and that filtering is making the thicker ice thinner, but stretching it out over a wider area. And when that happens, you have a process known as spatial aliasing. And it's really dominant in situations where you have a bimodal distribution of information, because now you've got two extremes that are being brought together to represent something that's not physically there, but representative of the average. And so in both the physical domain and in the frequency domain, you have a different set of characteristics that explain the same thing, but at different scales. So then you begin to ask, well, volume's conserved. In fact, I had some very good discussions with program managers about this. If the volume's conserved, what's the problem? The main thing is, what does it do to the climate data records? Because when you submit your data at the end of the day to the giant data agencies, you're not providing them with volume in your profiles. You're providing them with your thickness and your thickness distribution. And it's the thickness distribution that the modelers are using for their heat fluxes. And as I showed you, those heat fluxes have a big impact on our weather. So we ran an experiment where we looked at a bunch of different shapes as mathematical representations for waveforms. Here we see in bold the classic Gaussian, the classic Gaussian. Then we have this nice little linear, inverse linear, which modelers often use to smooth their data and bring it to different scales. And then there's a wider one. And then I point out in particular this little thing that looks like railroad tracks across the top is the infamous boxcar or running mean filter. And I ask you to remember that one in particular because we'll note something very special about that. And you can see that it's very simple to do an average. You just plug things in, you know the waveform, and you get an answer. Well, if we do this, not only with our little samples, but with the whole set of SEDNA data we had, where we were able to extract this, and if we take the thick black line plus its snow above, and we bring it into our little sampling system, you'll see that for the Gaussian, as you smooth it from 5-meter sampling to 100-meter, 200-meter, 400-meter, et cetera, you see that as you put a smooth function over it, you incur exactly what the toy model is showing. You end up moving the deep ridges up to shallow ridges, but wider ones. So they become wider, things get smoothed together, they combine forces, and things that were many little bumpy things become long, smooth things. And when you put it into a frequency domain, the volume's conserved. There is the little bit of a bimodal because of the extra thickness we couldn't get a hold of, and there's some little spikes, but everything remains below noise. However, the thickest ice is no longer represented. But we know that, so we just move on. However, when you put one of those running mean boxcar filters over this, it does more than just thin the ice. It actually begins to distort it. And in fact, in the frequency domain, it becomes so significant that you render artificial peaks that are substantially larger than the white level noise. And so what does this all mean? Well, what's happening is, just as I showed in the heuristic model, you have the thermodynamic mean thickness, and then you have these extra thick pieces of ice. And depending on how you sample it, and depending on the footprint you have, in fact, if you have a variable footprint and you start pooling together resources from a bunch of different instruments, you can create two distinctly different and yet seemingly smooth distribution functions. So that if you were to put an integral over the red one or the black one, you'd conserve volume, but the shape of your Rosetta stone is no longer the same. And the reason is all those ubiquitous little ridges and features and the different footprints and the different shapes of the instruments. And in particular, anytime you have bimodal distribution of information, whether you have two peaks, I'm thinking in particular the new ice and the existing ice, or cases where you have first-year ice and multi-year ice. Those all cause little bimodal peaks, and the averages can distort the thickness distribution. We also looked into it, thanks to my colleagues at the Danish Met Office. We said, well, what about with ice concentration? Could this occur as well? Here, it is the same bimodal problem, only in this case, it's the snow and ice, which are white, and on a 8-bit sequence, that's 255, and the open water is black, and that's 0. So now you start combining 0 and 255, and you get something in between. You get these grays. And in fact, if you filter it with a Bristol filter, then you get a 25-kilometer resolution, which is similar to the SSMI. And this is what SSMI sees. Now, when you look at a difference of these two, you end up with the same problem we had with the thickness. And that is that where there was a combination of white and black, you get very high differences in standard deviation between the low resolution and the high resolution result. And the importance of this is all those places where you had ice and water combined, that's all your ice edges, that's where your ships are navigating, that's where your the concentration of biology is often occurring. So while this isn't a big problem for the large-scale climate, as we start moving down into higher resolution, we're going to see a big impact as we try to connect what is going on at the large scale to what is going on at the human scale. And so, okay, this is a great academic exercise, Kathy, but get to the point, right? So are we just talking about, well, ridges and pieces and little trivial averages? I mean, the volume hasn't changed. It's not going to impact our estimate on global warming. It could just be that it's just a bunch of M's of ridges, and that's about all we need to care about. But let's take another example. And this one I'm going to show you is a vertical profile. This is of a different system known as the English language. And I'm going to apply a little instrument called a digital clock waveform. And I'm going to let this digital clock be an instrument that's going to measure this profile. And when it does, it's going to spit out exactly what it renders based on its spatial resolution. And as you can see, it does a very good job with the numbers, but there's a couple of letters have a little bit of trouble. In particular, you'll notice the R's and the M's and the N's have a little bit of trouble because the spatial resolution of my digital clock filter is bigger than the spatial features in the R's and the M's and the N's. And so we have an aliasing problem. In fact, if we're at the Super Bowl next week and the chef were to use this little filter and whoever won sent this message to his underlings to go buy more meat because they needed to double the meat, he would encounter a small problem in communication, specifically that the aliasing of the M to an H would communicate a completely different message, a message which, if you were not doubling your medium rare meat, but instead having half the meat at well done, you may encounter a bit of a conflict. And so my point here is that you have very little error in this little study I just did, less than 10%, well within range of good scientific collection, and yet these small little errors have introduced an aliasing which has caused a problem with the communication between and it's all due to scale. And so one of the ways we're looking at this is to first, well, we know there's a problem, so now how do we parameterize it? And in fact, you can do that with you can solve that by looking at a power law. And in fact, this algorithm that's showing up here is so simple that you can code it directly the way it's formulated on any computer to evaluate the scale of different instruments. And to show you as an example, let's say you're using a tapered linear filter for your data that's going into a model. You have a high resolution instrument and you want it to match your low resolution instrument or your lower resolution model. Well, if you take the shape, and let's say we're using an inverse linear because you're going to smooth it, you'll take your high resolution instrument, filter it, and you'll get it to match your low resolution instrument and prove that the two are the same. The only problem is that you've increased the resolution error as you've gone from this smaller scale to this larger scale. And in fact, if we look at the scale of this log plot on the y-axis, you can see that the error that's been increased as you've gone from, say, a 30-meter instrument to a 105-meter instrument is that you've increased error from about less than 20 centimeters to almost a meter, while heading 80 centimeters or so. So you can see there's a systematic increase as you go up in scale.
Kathy, it's Martin.
Yes. I'm wrapping up now.
Kathy,
That's okay.
it's Martin. We have 5 minutes left. Do you have many more slides?
This is the final 2 slides.
Okay.
Very good. So the impacts of this are, well, we know there's a problem with ship navigation on this. We need to know the thick ice. We definitely know there's a problem with modeling in this sense. And in terms of the ice volume, we don't feel there's any impact unless we're concerned about the deep ridges and the mass they contain. We do know that when we're comparing instruments, there isn't a problem unless we're concerned about having a matching between the two, and what we're seeing is a 1-meter resolution is going to be vital relative to the geometric resolution of the sea ice features. Ice concentration is not really a problem at the large scale. However, we are wondering about the impacts at the small scale. So in summary, there is a problem known as spatial aliasing, which can be looked at through a phenomenon known as resolution error, and that the bimodal cases are really causing an impact, and that there is a way to look at it and quantify it, especially if you have good statistics, a good footprint size, a sense of the footprint size, the shape, and oversampling. If you can oversample low-resolution information, you can make a lot of headway. And most importantly, and I think this is where a place like this, or perhaps the IARPIC data group would be very interested in this, is running means are all over the place. And whenever those are used, any form of non-Gaussian distribution is going to incur spatial aliasing in those very, very quickly. And that can really muck up the data sets. So there's a recommendation here of how to communicate among interagency groups and across all groups to figure out how we can at least remove those processes involving any kind of running average. And so with that, I open the floor to questions, and I thank you, and I'm curious about anyone's interest in the need for this type of information.
Okay, thank you very much, Kathy. Does anybody have any questions or comments for Kathy?
This is John Walsh. Am I audible here?
Yes, John, go ahead.
Yeah, I have one question for Kathy concerning this interpretation of the Arctic as a polar continental system. The coldest air masses, even before we got into this transition of the Arctic and its sea ice, the coldest air masses have always formed over the northern land areas because they don't have the benefit of that 1 or 2% open water or thin ice that the ice pack provides, the source of heat. So would it be fair to characterize the Arctic as continental polar with an asterisk, or just saying it's a variant of continental polar?
I think that's a really good point to bring up in a discussion, and I'm wondering, especially among climate scientists who are at the scales much larger than myself, what distinction we could begin to make about, how much open water. If it's 1 to 3%, is it still considered continental polar, or what moisture level in the atmosphere would quantify it as continental polar versus maritime polar? And maybe that's a good point for question and further discussion. And I do agree with the asterisk, because in the summer it's completely maritime. And so it might be interesting to see, perhaps we can develop an index in terms of gauging the, from a moisture perspective.
Okay, thanks.
If anybody would like to engage in that discussion, I encourage you to use the IARPIC Collaborations website, which is set up just for that kind of discussion. John, I think you wanted to add something. Sorry.
Oh, that was it. I think we can talk more about it later.
Okay, thanks, John. Any other comments or questions for Kathy?
Martin, I'll just chime in here. This is Jessica, everyone, and say a good place to start this discussion is down here in the comments section of the event page, or you can comment on Kathy's presentation directly.
Good, thank you for that, Jessica. Always good to get these reminders about the little tricks that are available to us on the website. Is anybody on mute, perhaps, and was talking to themselves, thinking they were asking a question or making a comment? Okay, it doesn't sound like anybody has anything else to add. In the interest of time, since we're just past 2 o'clock, I propose that we don't pursue agency updates to try and finish our agenda. Instead, we will do that next time, and perhaps even add in milestone updates to that. So I'm sure everyone's excited about that possibility. So come prepared with updates, either agency updates, or if you're a non-Fed, any update you would like to provide on some research that's relevant to the sea ice group, or some sea ice activity that's relevant to our team, please come prepared for that. And so I'd like to finish by thanking Kathy for her presentation. It's much appreciated, Kathy. It's amazing what we learn about the sea ice thickness distribution and how it can lead us down the wrong track if we're not very careful. I think this is important work, and it's important information that we all need to be aware of as we deal with questions of sea ice thickness distribution and extent and volume. So thanks again, Kathy. Thanks for everyone for calling in and joining us today.